Hello everyone. So this is the lecture 3 of the course Advanced Power System Analysis. So in this lectures we are going to just solve a Y-bus problem, and also we are just included the power flow solutions. What are the load flow solutions are there? So we will cover in this lecture. So before proceeding to the current lecture, so we have to just describe the previous lectures, what are the contents we already discussed. So in these lectures, we discussed the bus nomenclature with variables. So what are the types of buses are available in the power system? Why we are go for the Y buses classifications? Then we have also discussed the representation of the power system in terms of the single line diagrams. So and further at the last we discussed the formulation of the Y buses. So here we have to apply the nodal analysis, and we have already performed the empirical formula or steps of the Y bus formulation. So in the previous lecture. The basic objective of this lecture, we will going to solve a Y-bus problem using a single examples. Then after that, we have to give the active and reactive power flow equations in load flow analysis. And what are the power flow solutions, that is iterative solutions, are available in the literatures. Then we will just start, that is the first iterative load flow solution, that is called the Newton-Raphson methods. So this is the our objective of this. Here we are considered a example for the forming Y bus. So how we are going to build a Y bus. So in the questions they are giving a this is the a line figure, that is the 4 bus system. This is the bus 1, and this is bus 2, bus 3, and bus 4. So using these buses, all the bus 1 have the generator, bus 4 have the generator, bus 2 and 3 have the only loads. So based on the bus information, as we first calculate the Y bus. This is the line data of the given. So here the line means from bus to bus. So they have given this line data means they are starting from 1 to 2. This is the bus 1 to 2 means this transmission line data they have given. Series impedances, that in terms of the resistance per unit and reactance, and then also they have converted these series impedances in the admittance, conductance, and susceptance. Then total shunt value, that is the shunt charging admittances Y by 2 they have connected. So this Y by 2 we have to consider in terms of the pi network. Suppose this transmission line I am projecting here. This is the series data having the resistance and inductance, and here this is the Y. So this Y is transmitted into the admittance, that is in the pi network. So we have to consider the pi network. Why we are not considered the pi network, we already discussed. So in the first lectures, so this is the representation of the pi network of any transmission line. So this Y by 2 added connected here, and second Y by 2 connected to bus number 2. So finally we are applying the same algorithms of the Y bus for building algorithm. So we are getting this example. Here 0 means, this 0 means what happened? This 0 means there is no direct connection between these buses. Here also we are getting the 0. So these means there is no direct connection between these buses. Here this is the element 4 to 1. 4 to 1. You can see in this diagram from bus 4 to 1 bus that there is no direct connection. So there is no transmission lines means there is admittance will be 0. So here we are putting this one, and this one is the 1 to 4. 1 to 4 means just symmetry. As you know that the Y bus is the symmetry. So these elements are the symmetry of this element. So these are the symmetry. So here either we are consider 1 to 4 or 4 to 1. We are talking about the same line transmission line. So this is the way we can find out. So here we are just applying the Y bus algorithm. So you know that the Y bus is the when we are calculating these means diagonal elements means we have to add all the series admittances or shunt admittances are connected to a particular bus. So here we are Y11 means this transmission line admittance plus this transmission line admittance plus shunt admittance of this transmission line plus shunt admittance of this transmission line means 1, 2, 3. So this is the overall. And of diagonal transmission admittance values, we are simply putting their series values with multiplication of the -1. So here you can see this is the series values. So this one is the a Y bus of a 4 bus system. Here we are considering another example. So suppose this is the system they have given. Here also there is a 4 bus system. This one is the bus 1, this is the bus 1, this is the bus 2, bus 3, 2 and 4. So in between all the transmission line are represented only the admittances. There is a reactance will be 0. We are considering for the simplicity. And here bus 3 and 4 have the generator. With generator all the values are given. And this is the reference bus. So all the induced voltage, ABC angles they have given. So when we are converting in terms of the branch nodal applications base, you know that this transmission line voltage of VB and current, all these terms are we have to given. So this is the a simpler form we can convert. So we will going to discuss the how we are going to form this Y bus. So here you can see by using the branch values, here we are considering the how many number of branches are there. So based on this equations you can see the diagram. So we have to count how many branches are there. So we can found total 7 branches are there. So these branches are connected between the buses. Few branches are connected to itself. Suppose there is this branch, this is the YA for the generator buses. So these 3 and 4 bus have the generator. So these 3 and 4 have the generator buses. So only this is the we are getting. So this is also 4 bus have the generator, and rest branches we are getting from bus to 2 bus, and this is the admittances. So YC, YB are here given. So from this one you know that these branches elements are stored in a variables. So when then we have to apply the basic algorithms of the Y bus. So you know that diagonal elements are addition of the all time. When means from bus and I bus both are the equal, we can simply add. So this we have to apply this condition. So we are getting this term, and off diagonal you have to just put the same value. Suppose when from bus and not equal to 2 bus. So we have to just multiply. So we are getting the finally this form of the voltage Y buses. Now come to the power flow equations. What are the power flow equations we are going to use in load flow analysis? So here, before proceeding to calculate these power flow equations, we are just give the short representation of the polar representation of the transmission line, admittances, bus voltages and its current. So here you can see let this is the a rectangle representation of the any admittance value which is connected from I bus to J bus. So this can be, this one is the magnitude and this is the corresponding to angle. This is the polar form. This polar form can be converted into rectangle form using this formula. So here we are putting this the rectangle form. So this magnitude of Yij cos theta ij, this is the conductance Ij, And susceptance, what is the susceptance? So this susceptance you can see, this is the mod Yij sin theta ij, we have to consider the susceptance. Similarly, uh, phasor value of the voltage we can convert in the form of the polar. This is the polar form, and this is the rectangle form. So conversion here we have to see. So here we are going to calculate the active and reactive power entering the network at a particular bus I in terms of the polar representation. So here we have to consider the, you know that the P plus JQ or P plus IQ. Here we are consider the J is the imaginary part. So this is the PI minus JQ. We are taking the conjugate of the in left side and right side. So we are getting Pi minus JQi is equal to Vi conjugate into II. So this is the conjugate part. When we are representing the voltage in polar form, you have to convert into the conjugate value. So from the relation at the nodal equations, we can see the II, we are getting this one. We are putting this II here in this equation. So we are getting this one. So after the representation of this del Vi conjugate, so Vi is, we are getting the mod Vi into angle del I. So when we are taking the conjugate value, we are getting the Vi equal to value that is the mod Vi, and then angle is the minus del I. We are taking the conjugate value. So this is the del I. So this is the conjugate value of the Vi conjugate. So we are writing this is the conjugate value. So we are putting this value and converting. So as you know that in polar form, magnitude multiply and angle will be added. So here, what is the Vi angle? This is the minus del I. What is the Vn angle? So Vn we can write Vn is equal to, that is the magnitude of Vn and Vn and angle del n. So corresponding similar. And here the Yi we are written, so we can put here. So we are getting the theta In plus del n minus Yn. When we are separating real and reactive part, so we are equating the real and reactive part in the LHS side and RHS side. So we are getting the finally, this is the Pi, this is the active part, this is the general form. So this is the active part equation. Here capital N is the represents the total number of buses in the system. So this is the reactive power. So these two formulas are most important. So we are always going to use these formulas. This is the most important formula. Remember these two formulas. This because we are going to use in the load flow equations. This is the another representation how we are going to calculate the scheduled power. So this is the active power, real power flow we are getting, and this is the reactive power flow. So here representation PGI is this. We can say that this is the a generation power, injected active and reactive power at a particular bus I. So PGI or QGI are the generated power at a particular I, and PDI and QDI are the demand, active and reactive power at a particular I. So we can calculate the scheduled power. So here we are going to calculate the scheduled power for a particular I is equal to generated power minus demand power. So this Pi schedule is equal to PGI minus PDI. Similarly for the reactive power, Pi schedule is equal to PGI minus QDI. And what amount the active power and reactive power injected to the system, we have to calculate Pi. So Pi is, we have to calculate using the load flow analysis. So before proceeding this one, we have to calculate the mismatch powers in terms of the active and reactive. So mismatch power is equal to Pi schedule minus Pi calculated. So what amount of Pi schedule is equal minus Pi calculated, we can get the schedule power. So mismatch power. So this mismatch active and reactive power we are calculating, and we are putting the PI schedule values here. So we are finally getting this equation. So we are trying to minimize these mismatches. So this should be near about the 0. Then we can say it is okay. But it is the impossible to make del Pi and del Qi will be 0. So mismatch occurs in the course of the solving a power flow problems. If any mismatch, then we have to calculate the power flow equations. When calculating values Pi, Qi do not coincide with the calculus schedule values. So if Pi is equal to Pi this one, so we can say if we getting the 0, then there is no apply. We are not going to calculate the load flow. So here we have to consider the mismatch. If system have the mismatch, then we have to apply the load flow equations, or we are going to solve the load flow solutions using the Newton-Raphson load flow and some advanced techniques. So as we know that the power flow studies are implemented to a particular network when we want to for the planning and designing the future extension of the power system, or we want to know about the power system current conditions. So we have to determine the base operations of the existing systems. So the principle is the formation obtained from the power flow study is to magnitude and phase angle. So here we want only the magnitude voltage and phase angle of a voltage at each bus. So this is these two variables we want to calculate. Using these variables, then we can calculate the each bus, what are the active power and reactive power, what are the line power flow, what are the line losses, we can calculate. But the primary thing is we want to the each bus voltage phasor value, means magnitude voltage as well as angle. So here we are going to apply load flow solution techniques. So using these load flow solutions, we want to calculate only first, that is the magnitude voltage and angle of each bus voltage in terms of the phasor value. So phasor means these two quantities we have to calculate using load flow solution. So what are the methods are there? So here basically four methods are divided. So first basic method, that is the Gauss-Seidel method. Second is the Newton-Raphson method. Then decoupled Newton-Raphson method. Then fast decoupled Newton-Raphson method. So in our syllabus means advanced power system analysis. So we are going to discuss the first Newton-Raphson method, then decoupled method, then fast decoupled method. First, we are going to discuss Newton-Raphson. Gauss-Seidel means that is the UG level course syllabus, so we are not going to discuss Gauss-Seidel method. We are going to directly start Newton-Raphson method. Then there is a certain assumptions we have to apply on the Newton-Raphson load flow analysis. Then we can get the decoupled Newton-Raphson method. Then further we have to apply the certain assumptions. Then we can say that it is the fast decoupled method. Here all the methods are the iterative nature. So iterative means there is some problem in the convergence. So we due to this iterative, so they are taking the times during the computation. So we have to make it as a fast. So we have to take some assumptions based on our current requirements. So here this is the Newton-Raphson method. Here we are not considering the power equation, that is a simpler mathematic way we are trying to explain this basic aim of the Newton-Raphson method. So here we are considering the two variables, that is represented by x1 and x2, and b1 and b2 are the constant values. So here, as you know that if number of equations are unknown, so we have to solve these known equations. So we require at least same number of the equations. So suppose two variables here, so we require two number of equations to solve these equations. So here two variables we had considered, so two equations required. So here two equations means G1 and G2. So these two nonlinear equations. So this can be formulated as the H1 minus B1 is equal to 0, H2 minus B2. So where G1, G2 is the function of the X1, X2 and U. Where X1, X2 are the two variables we want to determine, and U R is the some independent control variables. So these we can represent. So zero such case, here we are just start going to use some initial case value. So we have to consider initial value. So initial value represented by this x1 of this 0. So these are the represents means initial values. So this is the initial values, or we can say that this is the iterations. So here we are just going to use this one. So this of means that is the iterative value, iteration, first iteration, second iteration, that is that. And initial values we are representing x1 star and x2 star. So here, so g1 x1 star x2 you can represent in the gi plus this one, and this is that. These are the initial values, or we can say that the starting value. This is the deviation in this values of the x1. Similarly for the x2. So using the Taylor series expansion, we are first here consider the G1, so we are going to expand. So using Taylor series we are following, then we have to have a G1x, then partial derivative, then first variable, then second partial derivative with respect to second variable, then second order, third order. So here we are considered only the first order. So when we are neglecting the first order, so we are a higher order, so we are getting these equations of the this G1 function. Similarly, we have to apply for the G2. This is the Newton-Raphson method for the G2. We can say that the G2 we have to apply here the Taylor series. So only we are consider the first difference equations order. So here this is the initial condition value. This is the first partial derivative. This is the first partial derivative with respect to x2, and we are neglecting the higher order. So we are just consider the derivative, partial derivative of order greater than 1. So we have to neglect these values. So we have neglected, we are getting these equations. Then we are converting these two equations in terms of the matrices. So this is the del G1 by del dx1, del G1 by del x2. So similarly here the del G2 by del x1, del G2 by del x2. So these are we are considered the initial values, means first value. So this is the deviations values, and we are getting these values. So here we are putting this one. So we are getting, this is the nothing but it's called as a Jacobian matrix. So here you can get the Jacobian matrix values using the partial derivative. When we are putting the its iteration values of the x1 and x2. Similarly, we are getting here. So here we have to repeat these steps. So you know that we can represent in the form of the, this is the matrix form. So J0 deletion, we have to calculate this correction terms. This is also called the correction terms. So these terms give us some errors. So what are the mismatch between the actual solution and starting guess value? So we have to add for the next iteration. So here we have chosen, this is the initial condition. We have calculated, this is the iterative values. This is the correction value. We have to add it each terms variable. So we are getting that this is the second terms, this values for the next iteration. So then we have to repeat for the next iteration. This is the second iteration we can say. So we have to put these values. We have to again calculate the Jacobian matrix. Then further we have to calculate the correction. Then we have to add. If these values are less than these correction values, magnitude values are less than chosen precision index chi greater than here we can say 10 to 1 minus 3, 10 to 1 minus 3. If less than, then we can terminate this equation. Otherwise, go for the next step. This is the overall algorithm of the Newton-Raphson method using this two variables. So same examples here we have to apply. So means Newton-Raphson method. So we have to consider here the two variables, that is the x1, x2, and we have to apply these x1, x2 variables means on the nonlinear equation. So what are the nonlinear equations? This is the nonlinear equations. This one G1 and G2. These are the two nonlinear equations. So here we have to first choose the initial value. What are the initial? U is the control variable. We have to consider that is equal to 1. And we have chosen the initial value x1 0 is equal to 0 radian and x2 0 is equal to 1 per unit. So, and chi value we have chosen the 10 power minus 5 for the termination point. So when we are choosing these value, first we have to calculate the Jacobian matrix. Jacobian matrix is nothing but is the partial derivative of the G1, G2 with respect to x1 and x2. So what is the order of the Jacobian matrix? You know that there are two variables, so order is the 2 by 2. So this is the G1, G2 partial derivative. When we are differentiating this G1 with respect to x1, so other variable we are treating as a constant value. So we are differentiating and putting these values. So we can calculate. Here you can see del G1 by del dx1 we are calculating. So we are getting this one. Del G1 by del x2 we are getting this value. So similarly for the G2 and with respect to this one. When we are putting these values x1 0 and x2 0 here, so we can get the numerical value of the Jacobian matrix. Then finally here also we can calculate the difference. So RHS side values, then we have to apply these conditions. Then we have to calculate del x1, del x2, then correct it and check the from the precision value. If we are getting the less than this value, this precision value, then we can terminate, otherwise go for the next iteration. So here we have to obtain like that. So after the fourth iterations, we are getting this condition. So we can terminate. So overall x1 and x2, this is the solution. Same process we have to apply here. This is the simplest example of the Newton-Raphson method in mathematical way. So here now we are going to discuss a comparative study about in between the Gauss-Seidel method. This is the Gauss-Seidel method. This is the Newton-Raphson method. So in between we are comparing. So there are four terms we have to consider. We can say that this is the merits and demerits. So as you know that Gauss-Seidel method you already go through in during your UG course, that is the power system analysis. So we are not going to discuss here. So if we are increasing the number of the size of the system, so we can say that the Gauss-Seidel convergence becomes very, so means number of iterations going to large. So it requires large number of iterations to reach the convergence. So particular convergence level, it requires large number of iterations. But the Newton-Raphson requires completely less. So computation time per iteration is less. Because here we have to consider, here we are not going to calculate the Jacobian matrix. But in Newton-Raphson it requires more. This is the, we can say that the demerits of the Newton-Raphson. But the merits of the Gauss-Seidel method. Because here we are not going to calculate any Jacobian matrix. We are directly using this one. So it is a linear convergence characteristics. When we are calculating the convergence characteristics, Gauss-Seidel gives the linear convergence, but it is the quadratic. So it is the x square something terms we are getting. So due to this convergence, number of iterations required for the convergence increase with the increase of the system size. Size is increases, so number of iterations increases. So computation times increases. So here convergence times is also increases. But in Newton-Raphson method, iteration is increases, so there is no depends on the number of iterations. It is completely independent. We can say the computation time is also same here. So convergence we are getting the fast. So Newton-Raphson method have these two merits. So we can say these are the merits. So and in terms of the memory, so Gauss-Seidel requires less memory, while the Newton-Raphson requires more memory. Why it is required? Because due to this Jacobian matrix, you have to partial deviates, and you have to put all the values. We have to store these values corresponding to each elements of the Jacobian matrix. Then you can solve this. So these are the merits and demerits, or we can say that the comparative analysis of the Jacobian matrix, the Newton-Raphson method and Gauss. Now we are just summarize the current lectures. Here we already discussed the Y bus. So based on the algorithms, we have to consider two algorithms method. Two examples for the calculation of the Y bus. Same algorithm we have to apply here for the two examples. Then we have to discuss the power flow equations. How we are going to calculate the Pi and Qi, active power and reactive power at a particular bus. So then power flow solutions, what are the power flow iterative solutions are available? Why we are going to apply the load flow analysis? We will discuss. What are its needs? We already discussed this one. Then we have to give the mathematical formulation of the Newton-Raphson method. So these are the methods we already covered in these lectures.